Okay, question 3. This one is very similar to the last one. The last one was all the thermodynamic and statistical properties for HCl. This is largely all the thermodynamic and statistical properties for nitrogen and oxygen, mostly for nitrogen. But there are a few questions right at the beginning that are roughly qualitative to give us a qualitative feeling for what makes a partition function large, what makes it small, and so on. So nitrogen and oxygen are very similar molecules, of course, but the oxygen is a little bit heavier. The oxygen has a molecular weight of 32, nitrogen has a molecular weight of 28, and that's going to make some difference. The bond strength is a little bit stronger for nitrogen, the bond length is a little shorter for nitrogen. Those small differences will make some difference in the translational partition function, the rotational partition functions, and in the vibrational partition functions, and we just want to review why those differences come about. Then in the latter part of the problem, we're going to do a whole bunch of calculations, all the same kinds of calculations we did last time for HCl. So first of all, the problem asks us to calculate the thermal de Broglie wavelength for nitrogen and oxygen. We have this nice formula, 1.746 over the square root of molecular weight, square root of temperature, in order to give us out a thermal de Broglie wavelength in nanometers, so 1.746 over the square root of 28 times temperature 300, and that turns out to be, for nitrogen, 0.01905 nanometers. So that's about 0.2 angstroms. It's pretty short. It's much smaller than even a single atom. But that's typical for thermal de Broglie wavelengths. For oxygen, so this was for nitrogen. For oxygen, it's the same thing, 1.746 over the square root of now 32 times 300, and that turns out to be 0.01782 nanometers. So just slightly shorter. It's shorter because the mass is higher, right? So a de Broglie wavelength, just to remind everybody what the de Broglie wavelength is in general, not the thermal de Broglie wavelength, but the quantum mechanical de Broglie wavelength, it's Planck's constant divided by mass times velocity. So if you have the same velocity but a heavier mass, you've got a shorter de Broglie wavelength, and that's what's happening here. The thermal de Broglie wavelength has the same properties. So the heavier the molecule is, the shorter the de Broglie wavelength, and then the partition function for N2, the translational one, is the volume over the cube of the de Broglie wavelength. And so, and the one for oxygen is the volume over the cube of the de Broglie wavelength for oxygen. And so the larger of these two is going to be the one with the shorter de Broglie wavelength, which means it's going to be the one with the heavier, with the greater mass. So larger translational partition function is heavier particle. And that's always true. I did this for two diatomics, two simple diatomics, but even if it were a protein or any other molecule, this is the center of mass contribution to the partition function. It's always present for every molecule, no matter how large, no matter how floppy, no matter what else it's doing, no matter how far it deviates from everything we've done so far, always there's a center of mass contribution. And the only thing it ever depends on is the mass of the molecule, and the heavier molecule will have the shorter de Broglie wavelength and therefore the larger translational contribution, translational partition function. All right, the next couple of questions, B and C here, ask qualitatively which will be the larger partition function for for the rotational partition, the rotations, and which one will be the larger for the vibrations. So B, for the rotations, remember the partition function for N2 here, let's say, is equal to the temperature divided by the symmetry factor and the rotational temperature. And remember that the rotational temperature is equal to h bar squared over 2 times I times k. So what matters is the moment of inertia. And for a diatomic molecule, the moment of inertia is the reduced mass times the equilibrium bond length squared. And so the moment of inertia is larger, and therefore the rotational temperature is smaller, and therefore the partition function is larger for things that have either large reduced mass or a long bond length. And so we're looking for molecules with either long bonds or two heavy molecules, two heavy atoms. Remember that no light atoms, actually. Remember that the reduced mass is always smaller than the lightest atom. And that means that if you've got even one light atom in the molecule, the reduced mass is small. You've got to have all heavy atoms before the reduced mass starts to get big. And short bonds will have smaller moment of inertia, therefore they'll have higher vibrational temperatures, therefore smaller partition functions, and so on. So, going by that understanding, N2 has lighter molecules, or lighter atoms, sorry, and a shorter bond, right? It's a triple bond, and therefore will have smaller reduced mass and a shorter r squared, or a smaller r squared, and therefore it will have the smaller moment of inertia, therefore it will have the higher rotational temperature, and therefore it will have the smaller rotational partition function, and O2 will have the larger rotational partition function. For C, it asks the same questions, but about vibrations. Remember that for the vibrational partition function, let's just write it out. Without the ZPE factor, it's 1 minus e to the minus theta v over t. It gets larger as the vibrational temperature goes down. So small theta v, same as rotations, means larger qv, and vice versa. So we're looking for things with small vibrational temperatures, and the vibrational temperature, remember, is equal to h times the fundamental frequency divided by k. So we're looking for small fundamental vibrational frequencies that will cause large QV, or larger QV. QV is rarely very large, but it will be larger if it's got a small fundamental frequency. A small fundamental frequency will give it a lower vibrational temperature. Remember that the frequency is 1 over 2 pi square root of force constant divided by reduced mass. So the things that make the fundamental frequency small are weak bonds. That makes the force constant small. And heavy atoms. Those are the things that make the reduced mass large. So basically weak bonds and heavy atoms means low vibrational temperature, means large vibrational Q. So N2 has a stronger bond and slightly lighter atoms. And therefore it'll have the higher fundamental frequency, and therefore it will have a higher vibrational temperature, and therefore it will have a smaller QV. And O2 will have the larger QV. All right, so that's the preliminaries. Now let's talk about the actual calculations. That's parts D and E here. Part D wants us to calculate the average energy for nitrogen. Now, all the rest of this is for nitrogen alone, not oxygen. And the CV for nitrogen. And it wants us to calculate all the independent contributions to that, too. Remember that the average energy has a translational contribution, a rotational contribution, a vibrational contribution, and then, in principle at least, an electronic contribution, and same for CV. And we want to calculate all those independently. So the translational contribution for nitrogen, nitrogen is a linear molecule, and that's all that matters, is going to be 3/2 NR. Does it say? I don't remember. Let's just assume that it's 1 mole. I'm pretty sure it's 1 mole. I didn't put it here. Well, let's go look and just make sure. So 3 here. It says for 1 mole of N2 at 300 K. All right. And here down below in the next part, it's at 300 K, 1 mole of N2 at 300 K and a pressure of 1 atmosphere. All right. So, then N is 1, and we have 3/2 R, which is equal to 12.8, if I remember right. Let's calculate it. I didn't do the individual ones. I did the, yeah, okay, so I just did the combination of translations and rotations. So 3/2 times 8.314 is 12.47. Oh, sorry, that's the heat capacity. I'll come back to that. So it's 3/2 nRT for energy, and that's 3/2 times 2479. No, 2494 at 300. I have both the 300 and 298 values memorized, and that is 3741 joules. That's T. The rotations then, it's linear, and so it's just nRT, and that's just, N is 1, so that's just 2494 joules. The two combined, let's not bother with that. It didn't ask for that. Then the vibrational contribution is going to be N times R times the vibrational temperature for nitrogen times e to the minus theta V over T over 1 minus e to the minus theta V over T. We expect this to be small, but let's put the numbers in. The vibrational temperature for nitrogen is 3374. So this is going to be 1 times 8.314 times 3374 times e to the minus 3374 over 300 over 1 minus e to the minus 3374 over 300. And that is equal to, I'm looking over here to see what answer I got. I didn't write, you can see the answer here. I didn't actually write out the answer, but it's around 0.01, and that's compared to the values for, sorry, that's for the heat capacity. I'm getting these guys confused. It's about 0.4. And that's compared to these thousands values for the translations and rotations, so it's negligible. as you would expect for a really strong bond with relatively light atoms like nitrogen has. So that means the total energy is then just the two translations, rotations, contributions, so that's 3741 plus 2494, and that is equal to 6236 joules. All right, now the CVs. So CV for translations is 3/2 NR, which is 3/2 times 8.314, which was 12.47, as I recall when we did that before, joules per K. CV for rotations is just going to be NR in this case, that's 8.314 joules per K. And the sum of those two, so the vibrations and translations to get, the translations and rotations together is going to be 20.8 if I remember right. Let's calculate that. It's 5/2 times 8.314, and that is 20.8 joules per K. All right. So that's the first two contributions. We expect the CV, the vibrational CV, to be small. That's going to be N times R times theta vibrational over T squared times e to the minus theta V over T over 1 minus e to the minus theta V over T quantity squared. Plugging everything in, that is going to be 8.314 times 3374 over 300 squared e to the minus 3374 over 300 divided by 1 minus e to the minus 3374 over 300 squared. And I did that calculation over here on the left-hand side. That's this part of the key right here. And you can see I didn't do it very accurately. I just said it was negligible, and because it's 0.01, and it is negligible, so let's just leave it at that. That means that CV is just the translations and rotations, 20.8 joules per K. Okay, that's it for the energy and for the CV for N2. Next, the problem asks us to do all the other properties, to calculate all the other properties. So the chemical potential, the Helmholtz free energy, the Gibbs free energy, the enthalpy, and the entropy. And so that's just a matter of going through all these calculations. Let's do that. It's always a good idea to start with the chemical potential because that's instrumental, very useful in calculating all these other quantities. Once you've got the chemical potential, you can get A and G and H and S pretty easily. So let's start with the chemical potential. As with HCl, the chemical potential is equal to RT log of the activity over the activity of microstates plus a ZPE offset, but we're setting that to 0 for this calculation. We didn't add it to the energy up here, for example, even though in principle it's there. For the present circumstances, we have P equals 1 atmosphere, we have N equals 1, we have T equals 300, and the activity is equal to N over V times 1 over the standard state concentration of 1 molar. And so that's equal to P over RT times 1 over the standard state concentration. That is 1 atmosphere over 0.08206 times 300. And that is equal to, I have that value calculated over here. What did I get? 0.04062. 0.04062 times 1 over C0 here, sorry, and that's unitless. So that's A. Now we need the microstate activity, and remember that's just the molecular partition function evaluated at C0. So the translations evaluated at C0, the rotations, the vibrations, and the electronic part. We have all this part, but the translational partition function we calculated above wasn't at C0, so we have to redo that calculation. So QT at C0, QT bar is what I call it. At C0, we have this nice formula. It's 0.46009 molecular weight times temperature to the 3/2 power if we're at a 1 molar standard state, which in fact we are here. So that formula works. That is 0.46009 times, for nitrogen, 28 times temperature of 300, all to the 3/2 power. And that gives it. It's calculated over here, I'm sure. I didn't calculate it separately. Well, let's calculate it then. It's 0.46009 times 28 times 300 to the 3/2 power, and that is 2.403 times 10 to the 5th is what I get. Yeah, 2.403 times 10 to the 5th for QT. We have QR, QV, and QE, so let's just plug that in. The activity of microstates is then 2.403 times 10 to the 5th times QR from above. Did we do QR? We didn't do QR. QR in this case is T. It's a linear diatomic with a sigma factor of 2, so that's sigma. A rotational temperature of, what's the rotational temperature? 2.88 K. So that's the rotational contribution. We didn't do the rotation, the vibrational partition function. That's 1 over 1 minus e to the minus theta v over T. And then nitrogen has no degeneracy in the ground state, so the electronic partition function is just 1. And that then is equal to our 2.403 times 10 to the 5th times 300 over 2 times 2.88 times 1 over 1 minus e to the minus 3374 over 300. This is going to be 1, I predict. And that will give us, now I did that calculation, the whole thing all the way out, and that's 1.251 times 10 to the 7th. And I hope that is reasonable. Let's see. This would be about 150 times that. Will give us 10 to the 7th, so I guess that's reasonable. I think that's right. I didn't make any mistakes over. I'm copying from over on this side, and I hope I didn't make any mistakes, but I don't think I did. All right, that's enough. So now the chemical potential is RT log of A over A mu 0. Chemical potential is 24, or RT is 2494 log of 0.04062 over 1.251 times 10 to the 7, and doing the calculator work on that gives minus 48.747 kilojoules per mole. All right. Notice that the biggest contribution, notice the minus sign first of all, that means it's a favorable chemical potential. notice that that's coming from this big denominator. It's coming from the activity of the microstates, or in other words, from the molecular partition function at C0. And the biggest contribution to that by far is the translational partition function. So most of this value is caused by the large number of translational microstates available to any molecule in the gas phase. Nitrogen isn't especially large, but it's a large number of states even for small light molecules like nitrogen more or less is. All right, that's the chemical potential. Next, let's do the Gibbs free energy. That's just mu n, right? That's the Euler relationship for Gibbs free energy. And so that's, and since n is equal to 1, that's just mu, minus 48.747 kilojoules per mole. So that was easy. A point that I forgot to make last time when we were talking about HCl is that look what we're calculating here. We're not calculating delta G's. These are not differences in Gibbs free energy from some reference state. These are absolute Gibbs free energies. That's unusual. It's hard to measure these. In fact, it's probably not possible to measure these. And so that means these numbers can't be compared directly to what's in the tables. The tables are all differences in Gibbs free energy from some standard state, right? The elements in their most stable state at 1 atmosphere and 298 K, that's what the delta G that appears in the tables, and that's not what this is. This is an absolute G. It's not a delta G at all. Next, let's calculate Helmholtz free energy. That's equal to, well, A is equal to U minus Ts, G is equal to H minus Ts, so that means that A is equal to, that means, let's see, that means Ts is equal to H minus G, which means that A is equal to U minus H plus G. U minus H is just minus PV, so that's G minus PV, or at least that's what I get, right? H is equal to U plus PV, so U minus H is just minus PV. Is that right? I think that is right. Yes, that is right. And so, if we have G, PV is equal to nRT, so minus nRT here. And so A is just equal to G minus, in this case, that's 2494, right? Nah. The RT is, and the N is 1. So it's just minus 48.747 minus 2.494, right? That's 2494 in kilojoules. And that is equal to minus 51.241 kilojoules. All right, that's the Helmholtz free energy. Next, let's do the enthalpy. H is equal to U plus PV, which is equal to U plus nRT, which is equal to the energy we got above. Where is that? Way up here. It's 6236. 6236. RT is 2494. And so that is equal to 8730 joules. And finally, the entropy. We have that, let's use G. G is equal to H minus Ts. We could do this with A too, or other ways for that matter. Well, actually, let's do it another way. We could use G, but let's do it this way. Using the standard Euler formula, we now have all the quantities we need. S is equal to U over T plus PV over T minus mu N over T. That's the standard Euler formula. And we have everything now, right? This is U over T plus PV over T is just NR minus mu N over T. That is equal to U is 6236 over 300 plus NR is just 8.314 minus chemical potential was minus 48,747, and I'm putting this in joules now. N is 1 over 300, and now if we do all of that, we get 191.59, and I put here over in the key, I compared that value, here's the 191.59, and notice I used H and G to do the calculation. In this case, we did it a different way over on the right-hand side, but here's the table value, 191.6, exactly agrees with the value we just calculated. That's satisfying when you get that kind of agreement. All right, that's the end of problem 3. We'll stop and do problem 4 next.